Hello, welcome to our talk, Conquering All Stores with Gimel. My name is Vladimir Bekvensky.
Hi everyone, this is Deepak. I'm a tech lead on a couple of products in the data platform services.
Hi everyone, this is Anisha. I am a senior software developer in data platform services.
And today we are going to look into Gimel. What is it? Why is it needed? What are the parts? And how do we use it? And then we will explore what are the next directions. Looking at the PayPal as a company, the PayPal over time was both growing organically, but it was also including other companies. And altogether, this united forces resulted in some quite impressive metrics when it comes to number of active accounts, the payment volumes, and the transactions. The data that is produced by a variety of systems is coming from the PayPal core and how we call them adjacencies, companies like Venmo, Zoom, Simility, and so on. The interesting thing about these systems is that they are requiring quite significant infrastructure to process this data. So there are large Hadoop clusters that include also GPUs, and currently PayPal is in migration to Google Cloud that will give more flexibility in running big data loads. The data loads and processing are also quite sizable. There are 200,000 yarn jobs per day that are processing over 160 petabytes of data in various formats in variety of stores. And PayPal is also one of the companies with the largest installations of Aerospike, Teradata, Hortonworks, Hadoop, and Oracle installations. And also this vast volume of data is processed through variety of compute from Spark, Hive, traditional MapReduce, and increasingly BigQuery. The interesting thing is that there is a fairly rich landscape. At the bottom of this slide, you can see the infrastructure, the lowest level. Originally, all of that was running in our data centers. We still have data centers, but now the interesting thing is that there is also growing element of public cloud. And what is interesting is that PayPal includes a variety of quite sophisticated mechanisms for predictive resource allocation and optimizing the load on the infrastructure. On top of that, there is a layer of a variety of data stores, from conventional data stores to streaming systems like Kafka. There are key value stores like Aerospike, the usual suspects in the Hadoop ecosystem, but also Teradata and variety of NoSQL stores for specialized use like Cassandra and Druid. All of this data access is heavily monitored, and security is at the heart of everything that we do. So all the way on the right hand side you see the logging, monitoring, alerting, security infrastructure that is pervasive through all of that. Above the data layer, there is a set of compute frameworks and APIs that allow us to process this data. And to the right hand side, you see UDC, which is the Universal Data Catalog, which is the metadata storage that describes every little piece of data in this data stores. And this is particularly important when it comes to security or privacy information. You need to know exactly where these data are. And the data stores are typically accessed through a particular API that allows you very fine control and security. On top of that, there is the Gimel SDK that provides the access to all of these different resources in a unified fashion. And the most typical use is that the developers would be using notebooks to access all of that, which is the variant of the Jupyter notebooks that are customized. So the highlighted areas represent the Gimel. So the set of capabilities for compute, for understanding and recognizing where is the data, different data elements. And the beauty of the Gimel SDK and notebooks is that it allows uniform access to all of these different stores, regardless of what is the underlying technology. All of that is exposed as a SQL that variety of users that you can see on the top, from developers, data scientists, and so on, can understand and productively use. With that, we'll go to the next section, why Gimel.
Thank you, Vladimir. As the PayPal business grew tremendously, so did the data. Our data exploded, and the landscape of data became extremely complex with a variety of stores deployed across the ecosystem. So, with this, empowering all our data users and data applications to access data very easily became a big challenge. So, we embarked on the journey to democratize data in PayPal in 2017 and 18. If you take a simple example of reading or writing to any store through Spark, not to go into the details of the code, but this boilerplate code depicts the complexity that exists for any new application developer. If you apply this across the data stores that we have in the ecosystem, not restricting to these, data access code is really cumbersome and fragile in many ways. Just within the realm of Spark, there are multiple ways to run the code. You could write a Spark SQL batch or Spark batch through programmatic ways, or a Spark streaming or API access in the form of thrift servers. Beyond this, when it comes to writing a code, the developers have the choice of writing the code in Scala, Python, Java, or expressed through SQL and so on. Now, if you put this into the perspective of an application lifecycle, onboarding the data app first time requires somebody to learn about the data stores involved. Let's take the example of writing a code in Spark that reads from Kafka, writes to HBASE, and you're writing a batch application or a streaming application more predominantly. In this case, the developer needs to learn how to access Kafka, how to write to HBASE, not only that, some of the Spark paradigms. And once the code is written, the time is spent on optimizing the code, building it, shipping it, and then running it in production. What if the Spark version were to change? Let's say we are running Spark 2 and we are moving to Spark 3, or we had Spark 1.6 before and we moved to Spark 2x. Now, the entire life cycle of learning about the changes, coding for that, and then optimizing, building is yet another life cycle. If the storage API changed, that involves the entire lifecycle cost. Same thing with the connector. If we are using a Hortonworks connector for Spark and then something upgraded in the connector, the lifecycle is again a full cost. Just within the example of PayPal realm, we have this multi-data center system where the systems can be migrated across the data centers, which requires us to change configs. This could incur the cost of, again, the code breaking and the developer learning the code, rewriting this whole cycle. The story is no different if I were to move my target sync from HBASE to, say, Elasticsearch. The code that was written before has been broken and it has to be redone again. So the reasons can be many more, but the problem is still the same. For every small change that happens in the ecosystem, there is a cost that this particular application lifecycle incurs. In the end, the developer has actually spent probably 5% writing the data application's business logic. The remaining 95% of the time is mostly spent on maintaining this application. We wanted to get to a state, and we've achieved it to a certain successful extent, where the developer can basically write the code once, and regardless of what changes behind the scene, these dimensions should not affect the application lifecycle. This is where Gimel helped in providing a unified data API, which we will see soon. At the same time, we realized that a major set of users were missing in the form of SQL users, so we also created Unified SQL API. While we were able to create a simplification of data access, we also came into the problem of how do we make sure we get visibility on all the applications that are running Spark, regardless of whether they are Spark SQL, Spark Batch, Spark Streaming, that are all using the ecosystem. At the same time, with the evolution of unified data catalog and data classification that provides sensitive element exposure, the applications required access to this in the form of APIs. Every application started writing its own integration to the unified data catalog. Security is ubiquitous to PayPal, and it does not just apply within the realms of every data store. It also applies in the way the users access data within the compute realm. Let's say in Spark, when somebody accesses specific data, we need to have a way to not just rely on the store itself, but also have an Uber security. With the emergence of governance and privacy, we need to make sure that everybody or every application that is accessing data has this out of the box plumbing to apply redaction if required. If we were to turn on redaction on all the sensitive elements, we should be able to do it with one click or one switch rather than having to rely on running a program across the organization. And finally, one of the big problems is predominant across the ecosystem is every platform operator, be it Hadoop or Kafka or database, they would like to instrument some form of interceptors or libraries that emits these tiny little logs or audit trails which can be used to gain visibility into the operational aspect of the stores. These were becoming emerging problem for a large organization like PayPal, and we not only added data access API but also added this unification of various other kinds of touch points that are required to run a large platform or ecosystem at scale. Just to double click on one of those areas, you can see here each of these stores have their own way of auditing SQL logs. If we were to get a unified view of a Spark application that is accessing Hive and Teradata and also maybe Elasticsearch, it's very hard to get that unified view today without having to instrument something special. The same thing with the problem of a platform operator. If a platform operator had to instrument certain libraries that were to emit logs, the platform operator works with every data application or developer to instrument these libraries, or there is a recipe that every app developer uses. Now, if some of the recipes changed, all these users would either require to work with the operator of the platform or the other way around. This becomes a very cross-product problem where we have multiple parties working together to just solve one simple problem. So putting it all together, these are the kind of problems that we have solved by introducing not just a unified data access, but also some of the other ETs. For example, you can see here one simple application that is accessing some data must be able to not only abstract data access by simple form of SQL, by inserting into Hive, select from Kafka and join MySQL, for example, but also get the other capabilities out of the box like access to data classification or a catalog, provide ways to send alerts out of the box without any additional cost, securely access data and apply redaction if required, if it has to be turned on. At the same time, providing visibility for the operators in the form of embedding their interceptors and without exposing those complexities to the data users. So with that, I'll move on to show some practical examples of how Gimel can be used. Followed by that, we'll have Anisha walk us through the depths of Gimel. Before we take a look at the Gimel APIs, a quick reference to the GitHub repo and the documentation. The best way to get to this repo is by typing gimel.io on the browser. It should take you to the documentation. Followed by that, it should also lead you to the GitHub repository. For the sake of demo, we are going to be using Google's Dataproc cluster with Jupyter notebooks. We'll be using Spark 2.4.7 with Scala 2.12, which is what Gimel has been combined with. And in the interest of time, I'm not going to be running the code and looking at the data. I'll just walk you through the APIs. So we're going to add Gimel's core library along with Spark's BigQuery support library so that we can play with BigQuery. Gimel has been written with Scala. So Gimel has the dataset class which exposes the read and write APIs. At the same time, the same dataset class can be referred through Python lingua as well. Depending on the choice of program, Gimel can be used either in Scala or Python. The pattern is same across all the stores if you would like to read data with Gimel. The read API in the dataset class takes in a dataset name followed by an optional key value pair options which controls the behavior of the dataset read API, and the result is a data frame which is the representation of the data. Once you have the data frame, the user will work with the business logic, and once the data is transformed and it needs to be written somewhere, the user can use the write API to write data to a particular dataset by passing the data frame as the parameter along with an optional key value pairs. Now you might observe that I am just passing a string as a dataset name. Somewhere underlying in the code, this is being transformed into a configuration resulting in a connector that will be generated to access the data. Another thing to observe is, because we want to democratize data, we have always strived to make sure a SQL reference is also available for the reads and writes. So the same dataset can be either read through the read API or by running a select star query. Similarly, to write data into any dataset, we can use the same SQL format that we use in Spark SQL by issuing an insert into a dataset, select some transformation, and then do other things that you would usually apply in SQL, like joins or where clauses. A couple of things to notice here is the options that are usually passed in the data API are converted to set commands in the SQL, and the writes are converted to inserts, the reads are converted to select start from. Under the hood, the catalog provider does the magic. So there are three types of catalog providers in Gimel. There is a user catalog provider, there is a UDC, and then there is a Hive catalog provider. UDC is nothing but PayPal's unified data catalog. It's an enterprise catalog which exposes APIs. These APIs provide all the configurations about the data storage system and also all the information that you need to read from the dataset. So all that information is used by Gimel under the hood when you issue a read or a select API. Now, if you look at the catalog provider Hive, in any Hive cluster, we can create a simple Hive table and pass all those configurations that are provided by UDC in the form of table properties. You can observe here that by passing the gimel.storage.type GCS, when I issue a read API call, by gleaming into the storage type, the GCS connector in Gimel is invoked. At the same time, I could just change this to BigQuery and read in the read API. This would result in a read from a BigQuery table. This is the magic that's happening under the hood by connecting the catalog provider to the actual data connector, which is going to read the data or write the data. Now, the other thing that our users use predominantly is the catalog provider user. This is mostly an ephemeral configuration that runs within the lifecycle of a Spark application. It's very useful to test or debug in a local environment where there is no Hive or UDC. Just to summarize, there is a read API, there is a write API, and there is a SQL, and there is this concept of catalog provider which works under the hood to translate these abstracted calls to actual code that needs to run on the storages. The details of all of this will be covered by the coming slides, where Anisha is going to walk us through the anatomy of catalog provider and the anatomy of SQL. And also we'll be covering a little bit on the Spark thrift server, which has been enhanced to form what we call as Gimel thrift server.
Thanks, Deepak. Now let's do a deep dive into Gimel implementation. As explained by Deepak before, in order to read or write from any data storage, a developer has to do some research about different connectors and also how to use them in a most efficient way. In order to solve this problem, Gimel provides an abstraction using unified data API, which is dataset.read and dataset.write. Along with this, it provides a SQL access over these data storages. With the help of this, not only application developers but also the DBAs and product managers who are not aware of the Scala or Java code can easily access data from these storages. So basically, with this, all the boilerplate code for connecting to different storages is abstracted out, and developers just need to focus on the business logic. Now let's look at an example of reading from two different storages, Kafka and Elasticsearch. Now with the help of unified connector configurations, storage specific properties can be passed to the dataset.read through arguments, so that even if we need to add a configuration or update the data storage itself, user just needs to change these configurations without worrying about the underlying implementation of dataset.read API. These configurations can be passed to the API in different ways using catalog provider. So there are various options in Gimel today for the catalog provider. First is user. In this option, dataset properties are passed as JSON. But as you can see, every user will need to have their own configurations defined in their application. So there is no shared repository of where these configurations are stored. That's why we introduced Hive Catalog Provider, in which all these configurations for various datasets are stored in Hive Catalog. But still, we can have multiple Hive clusters, and to maintain these properties among different clusters can be challenging. To overcome these problems, we added an option of plugging in external metadata services. In PayPal, we have a unified data catalog which scans all the storages within PayPal and stores the metadata for different data sets into a centralized repository. So basically, the idea of data catalog provider is to plug in your own implementation for the metadata service. Okay, now let's look at how a Gimel SQL works. So SQL can have a select clause, an insert clause, and a bunch of runtime properties using set commands. Now using our code gen, the select clause is converted into dataset.read call, insert into is converted into dataset.write, and all the runtime properties which are set before the query are passed on as arguments to these APIs. Now once we have the APIs, read and write APIs, the catalog provider is called to fetch the dataset properties for this dataset. And based on the storage type attribute of this dataset, the respective dataset object is fetched from the dataset factory. And these storage specific dataset objects have a read and write implementation for their own connectors. So for example, Kafka read implementation has a Kafka consumer, and Kafka's write implementation will have Kafka producer code. In Gimel, we have used a combination of open source connectors and also some of the in-house implementation. So this is how a Gimel SQL is parsed and converted into a Scala code behind the scenes. Now let's look into Gimel Thrift Server. As most of you might be aware of Hive Server 2, which is a long-running service based on Apache Thrift concept, which is used to run low-latency Hive queries. Spark Thrift Server is an extension to Hive Server 2, with the difference being Spark as a compute engine instead of Hive. Now with both the services, we get a power of running low-latency queries, but still we don't get an abstraction to read or write from different storages. So we added a support for Gimel into Spark Thrift Server so that we get a power of running low latency query from Thrift Server and the power of Gimel to read or write from from different data storages. We also added some PayPal specific features and integrated it with Unicatalog. Okay, now let's look at a scenario where a user needs to read data from Hive through SQL. So in a basic scenario, a user will request for a Spark session, wait for it to get created on Spark cluster, and depending upon the cluster capacity and traffic, the user might need to wait for a couple of minutes. Once they get a session, the query gets submitted to the Spark session and they're able to read from these storages. In this case, external applications like Node.js are not able to access the data from these storages as they need to connect to the Spark cluster to get the Spark session. So basically, this involves some latency in running the queries. With Gimel Thrift Server, user need not wait for creating the separate Spark session on the cluster. Instead of that, they can directly submit the query to a long-running Spark session which is maintained by the Thrift Server. In this way, they are able to read from different storages right away. With this, even the external applications like Node.js can connect to the Thrift Server using JDBC and can access these big data storages. So in this way, with the power of Thrift Server to run low latency queries and Gimel, which abstracts the access to different storages, we are able to run low latency queries over these data storages. Now let's look at the next steps.
In terms of next steps, PayPal is on the path to cloud, so we are going to start adding support to the various stores that exist in cloud. At the same time, we would like to also start supporting these cloud stores from the SQL perspective so that we can continue to support the SQL community. While we do all of this, one of the learnings is as we continue to abstract the complexities of the stores and the compute, the actual workload and the complexity of optimizing these different queries under the hood has become a challenge. So we'll be spending a lot of time on preempting these runaway queries or optimizing them or putting query guards around them. On the wishful side, we would like to expand our catalog provider support to Google's data catalog. While we do all of this, we want to also tackle the graph database abstraction. Finally, we would like to make sure that we integrate with Spark's machine learning library and also add support for NLP. With that, I would like to summarize by sharing our GitHub repo. You can find that in gimel.io. And also, after this talk, we can continue our discussion and expand on further topics by chatting on Gitter. Now we will open for questions.